All right, let's dive right in. Today, we're going to pull back the curtain on the invisible forces that power pretty much everything around us. We're unlocking the secrets of electric potential and capacitance.
I know, it sounds a little weird, right? But seriously, the answer to this question gets to the absolute heart of how electricity works. Stick with me because this analogy is the key to understanding a really powerful concept.
So, first things first, we need to get our heads around what makes charge want to move in the first place. A great way to think about it isn't so much a flow, but more like pressure, an electrical height that charges can fall from.
Okay, let's really break this down. If you look on the left, you see something we all understand, lifting a ball. You have to fight gravity, you do work, and that ball now has potential energy. Now look to the right. That's the electrical version of the exact same thing. When you move that positive charge against the electric field, it's like you're pushing it up an electrical hill. You're doing work, and you're storing that work as electric potential. So here's the official textbook definition. Electric potential is just the amount of work it takes to drag a single positive charge from some starting point, you can think of it as sea level, all the way to a specific spot in an electric field.
And this is where it all comes together in one super clean equation. V equals W over Q. The potential, V, is the work done, W, divided by the charge, Q. So it's not about the total work. It's about how much work you have to do for each and every little packet of charge. That simple ratio is electric potential.
Okay, so we get it. Potential is like electrical pressure. But what good is that pressure if you can't, bottle it up and save it for later when you actually need it? This brings us to the next big idea. Let's talk about capacitance. And honestly, the best way to picture it is just as an electrical bucket. But instead of holding water, this bucket is built to hold electric charge. So what capacitance really tells us is how good something is at storing charge. For a given amount of that electrical pressure or potential, how much charge can we actually cram into our bucket? That's capacitance. Now, what's really wild is how a simple physical shape can change everything. If you just look at this sphere, you can see that its capacitance is tied directly to its radius. The idea is so intuitive. A bigger bucket holds more water, and a bigger sphere holds more charge. Simple as that.
Right, because in modern electronics, just making things bigger isn't really an option. Everything needs to be smaller. So, is there a way to cheat? A secret ingredient we can add to our electrical bucket to let us pack in way more charge?
Oh, you bet there is. And that secret ingredient has a name: dielectrics. These materials are the key to making the compact, high-capacity storage devices that we use every day. Let's see how they work their magic. So let's start with a really basic capacitor. Just two metal plates with nothing but empty space in between. When we charge it up, a pretty strong electric field forms between them. We'll call this our baseline, our E naught. Okay, now watch this. We're going to slide a piece of dielectric material, something like glass or plastic, right in between those plates. Instantly, the molecules inside that material get all rearranged, they polarize, and they create their own little electric field that actually pushes back against the main one, weakening the overall field inside. And here's the punchline. Because the field is weaker, the overall electrical pressure drops. That means you can now cram way more charge onto the plates to get back to the same voltage you had before. You've basically made the bucket bigger without changing its physical size. The capacitance just got a massive upgrade. All right, so we've mastered building one awesome capacitor. But in the real world, in actual circuits, you almost never use just one. So how do we combine them to get exactly what we need? Well, the first way is to put them in series. Just look at the diagram. They're lined up one after another, like cars in a single-lane tunnel. The charge has no choice but to go through each and every one of them in turn. The other way to do it is in parallel. And you can see right away how different this is. The path splits, right? It's like a river splitting into several smaller streams. The charge gets to divide up and flow down each separate path. This table lays it all out perfectly. When they're in series, every capacitor gets the exact same amount of charge, but the voltage has to be shared between them. And weirdly, the total capacitance actually goes down. But in parallel, it's the opposite. The voltage is the same for everyone, but the charge splits up. And the best part, to get the total capacitance, you just add them all up. So simple. So, we've covered the theory. Potential, storage, circuits. Now, let's get to the payoff. Why do we even care about any of this? This is where we connect the dots from these abstract ideas to real, actual power.
It all boils down to this one beautiful, elegant little formula. The energy stored is 1/2 times C times V squared. And you gotta pay attention to that V squared part. That's the secret sauce. It means if you double the voltage, you don't just get double the energy, you get 4 times the energy. That's how these little things can pack such a punch.
Don't let how small that equation is fool you. What it's really describing is an incredible superpower. The ability to gather up energy nice and slow, and then bam, release it all in a single powerful instant.
And you see this superpower everywhere. That blindingly bright flash on your camera? That's a capacitor. The life-saving jolt from a defibrillator? Yep, capacitor. They're smoothing out the power in your phone. They're the basis for your computer's memory. They even help you tune in to your favorite radio station. They are literally everywhere. You know, that quote on the screen really nails it. It might sound dramatic, but this ability to store and release energy on demand, it really is the invisible heartbeat of almost all modern technology. And that leaves you with one last thought, doesn't it? If these tiny, simple components are so fundamental to our lives, it just makes you wonder what other amazing, fundamental forces are out there silently shaping our reality, just waiting for us to figure them out.